Kepler's three laws of planetary motion. The first law is the law of orbits, that all planets move in elliptical orbits with the Sun at one focus. The second law is the law of areas, that a line that connects a planet to the Sun sweeps out equal areas in equal time. The third law is the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. And this is the only one of Kepler's laws that is actually in the syllabus. For any two satellites orbiting the same body, r cubed 1 over t squared 1 equals r cubed 2 over t squared 2. Newton's law of universal gravitation states that every particle of matter in the universe attracts every other particle of matter in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. As an equation, Newton's law of universal gravitation can be written as capital F equals capital G m1 m2 on d squared, where capital F is force in newtons and is quite often written as F subscript G for force due to gravity. M subscript 1 and M subscript 2 are the masses of the two bodies in kilograms. D is the distance between the two bodies in meters, and capital G is the universal gravitational constant. The orbits of the planets around the Sun are very nearly circular. A circle is a special case of an ellipse. Over the course of a full orbit, the average velocity and altitude of an object in an elliptical orbit are identical to those of a body in a circular orbit. Objects in uniform circular motion have a constant tangential velocity, shown by the red arrows, and a constant radial acceleration, shown by the blue arrows. For an object undergoing uniform circular motion, the tangential velocity, centripetal acceleration, and centripetal force are given by v equals 2 pi r on t, a equals v squared on r, and f equals mv squared on r, where v is the tangential velocity in meters per second, capital T is the orbital period in seconds, r is the radius of the circle in meters, m is the mass of the object in kilograms, and F is the force in newtons. By equating centripetal force in uniform circular motion with the force calculated from Newton's law of universal gravitation, we can derive the relationship r cubed on t squared equals capital G capital M on 4 pi squared, where capital M is the mass of the central body in kilograms, and G is the universal gravitational constant. R is of course the radius, and T is the period of the orbit in seconds. Low Earth and geostationary satellites. Low Earth orbit satellites. Low Earth orbit satellites orbit at an altitude of between 200 and 2,000 kilometers above the surface of the Earth. They have an orbital velocity of approximately 7.78 by 10 to the 3 meters per second at 200 kilometers altitude, and they orbit many times in a day. Geostationary satellites orbit above the equator at an altitude of approximately 36,000 kilometers. Orbital velocity for geostationary satellites is approximately 3.07 by 10 to the 3 meters per second, and by definition have an orbital period of 24 hours. Low Earth orbit satellites have higher orbital velocities, shorter orbital periods, and lower altitude above the Earth's surface than do geostationary satellites. This table summarizes the property of low Earth and geostationary satellites. Low Earth satellites have an altitude of 200 to 2,000 kilometers, whereas it's approximately 36,000 kilometers for geostationary satellites. Low Earth satellites have velocities ranging from 7.12 to 7.78 by 10 to the 3 meters per second, whereas geostationary satellites have velocity of approximately 3.07 by 10 to the 3 meters per second. And low Earth satellites have a period of between approximately 1.5 and 2.1 hours, whereas geostationary satellites have a period of 24 hours. Low Earth orbit satellites experience drag from the Earth's outer atmosphere. The orbit of the International Space Station, for example, which orbits at 400 kilometers altitude, decays by approximately 2 kilometers per month. The Slingshot effect. The Slingshot effect is a non-contact elastic collision between a spacecraft and a planet. Both momentum and kinetic energy are conserved. The Slingshot effect results in a change in the velocity and/or direction of the spacecraft, usually both. The planet or other body loses kinetic energy equal to that gained by the spacecraft. The change in the velocity of the planet is insignificant, as the mass of the planet is very large compared to that of the spacecraft. Re-entry. When undergoing re-entry, space vehicles experience heat caused by friction and by shock forces, mostly by shock forces, and g-forces due to deceleration. Atmospheric entry altitude is defined as 100 kilometers. Most space vehicles are designed with a blunt leading edge to create a shock wave which keeps heat at a distance from the vehicle and slows the vehicle's fall. Heat shields are used to protect the vehicle. Too higher g-forces can cause blackout and even death of the crew. Ionization blackout is caused by hot ionized gases which block radio communication, although actually with modern spacecraft this is not a problem. Re-entry angle. The steeper the angle of re-entry, the more rapid the deceleration, and the greater the heat generated, as well as the g-forces experienced by the crew. Too steep an angle may cause the spacecraft to burn up, or it may be damaged or the crew injured or killed by too high g-forces. Too shallow an angle may cause the spacecraft to miss its landing zone and expose the heat shields to hot gases for longer and potentially lead to failure in the heat shields. Much too shallow an angle may cause the spacecraft to skip or bounce off. Thank you for watching.